Va bene, va bene. Ciao, ciao, ciao. Good morning. Sorry for the delay, but also today we had some problems with the internet, so we have solved only now these problems. So we can start now. One moment, sorry. Okay. We can start with the goal definition step of LCA. In the last lesson, we have seen the first points about the goal step in the LCA. In the LCA analysis, we have seen the intended applications of the results, the limitations of the study. So the last point, the last important point in the goal definition step is the definition of the target audience of the study. To whom the results of the study are intended to be communicated. In this case, for an LCA analysis, we have the possibility to define different subjects interested to this kind of analysis. In fact, typically the main target audience is represented by companies, but also, for example, we can have other potential target audience, such as consumers, government. If you want to use the LCA study, for example, to define new regulations. So the target audience it could be very different, and also according to the target audience, the final aim of the study could change, because if the target audience is a company, probably the main aim of the study is the comparison of a product with an average market product, in order to define which product is characterized by the less environmental impacts. So the target audience in general should be defined at the beginning of the study. In the second part of this first phase, we have to define the scope of the study. In particular, this step of the LCA is a very important step because in this case we have to define the hypothesis of our study, and in this case we have to define in detail 6 main points according to the ISO standard 14044. The first point is the function, the definition of the function of the system. The second point is the functional unit of the analysis. The third point is the definition of the system boundaries of the LCA study, and then the last 3 points are the definition of cutoff rules, the data quality requirements, and how we intend to model multifunctional processes. Then in the next slides we'll see the definition of a multifunctional process. But now we can say that these 6 points are very crucial if we want to define correctly the hypothesis of the LCA study. So we can start from the first point about the function of the system. The function of the system could be an ambiguous, could have an ambiguous meaning, but I think that we can understand the meaning of this term, of this point, by reading some examples in this slide. For example, we can consider the last section of this slide. No, a typical example to understand the meaning of the function of an LCA study is this one. For example, if we want to compare, if we want to use the LCA study to compare the environmental performance of 2 different products, such as a tablet and a newspaper, in this case, we have a typical example for which the definition of a function is very important, because in this case the function of these 2 products is different. It's not the same. These 2 products are not characterized by the same function. In fact, the main function of a tablet and of a newspaper, the main function is that these 2 products are news media. But the problem is that the tablets provides more functions than the newspaper. In fact, with the tablet we have access to other websites, word processing, other software, and so in this case, if we want to carry out an LCA study for this scope, for the comparison of these 2 products, tablet and newspaper, in this case the comparison could be not meaningful, because the function of these 2 products is different. On the other hand, for example, if we want to compare 2 different energy technologies, in this case, for example, two different energy technologies for electricity production by using, I don't know, two different sources, a fossil source and a renewable source. In this case, the function is the same. And so in this case, the application of the LCA study in order to compare the environmental performance of these two products, it could be considered is right in this case, this comparison, because in this case the function is that these two products they provide of enabling the delivery of electricity, for example, to households. The definition in general, the definition of the function of a product is very important when we want to use the LCA study to compare the environmental performance of different products. In this case, the definition of function is very important, okay? So, this point is a very important point in order to obtain a meaningful comparison between our products. As regards the second point in the scope definition step of the LCA study, the second point is the definition of functional unit. Also, functional unit in an LCA study is a very, very important point. In this case, we can read in this slide that defining a functional unit can be quite difficult. But we can understand the functional unit as a sort of a unit of measure of our study. In fact, when we calculate the environmental impacts associated to our product, for example, if we consider the environmental impacts in terms of greenhouse gas emissions, in terms of climate change, in this case, our impacts are defined in typically in kilograms of CO2 equivalent. But this value of greenhouse gas emissions has to be referred to a functional unit. In fact, if we want to use, if we want to analyze the, I don't know, the environmental performance of a, in this classroom, for example, of a window, we have to define the functional unit. We have to define the reference of our final results. So, for a window, the typical functional unit could be, for example, one piece of window. For a computer, one piece of a computer. But for example, if we want to analyze the environmental impacts of, I don't know, photovoltaic, solar energy, photovoltaic energy, electricity by photovoltaic. So in this case, the functional unit, so the reference of our final results, in this case could be, for example, 1 kilowatt hour of electricity produced by photovoltaic panels. So the functional unit is the reference of our final results. So it's important when we decide to carry out the LCA study to define this reference. This reference is important mostly when we want to compare two different products. But the selection of the functional unit could not be easy in all cases. For example, in this slide, we can see an example for which the definition of functional unit could generate some problems. For example, if we want to compare the environmental performance of paper towels and with the hand dryers, in this case, the function of these products is the same, and the function of these products is to dry hands, for example. Okay, but it's very important if we want to compare the environmental performance of these two products. It's very important to define the reference of the results, the functional unit. In this case, for example, a typical functional unit could be the number of pair of dried hands by using paper towels or hand dryers. On the other hand, if we choose different functional units, probably we cannot compare in a right way the environmental performance of these two products. Another example, another interesting example about the selection of a functional unit is the, for example, in the food when we refer to food products. For example, if we want to compare two different milks produced by two different companies, in this case, the typical functional unit that can be used to compare the environmental performance of these two different milks could be 1 liter, for example, of milk. This is an option. This is an option to reach a meaningful comparison between these two milks produced by two different companies. But we can think that these two milks are characterized by different properties, by different contents, for example, by different content of, for example, fat or protein. And so in literature, typically, if you read a scientific paper about the comparison of two or more than two milks, typically the functional unit in this case is not simply 1 liter of milk, but it's 1 liter. This 1 liter is modified with a formula, with an equation, by considering the fat and protein content in the milk, in order to comprehend, in order to include in the functional unit also the quality of the food product. So this problem in the selection of a functional unit is typical for food product, but not only for food products, but this problem we can have this problem also in other fields when the technical properties of the products can change, can influence the comparison between the products. Okay, so the definition of functional unit and the difficult to define the functional unit depends on the function of the product. So about functional unit, and according to the ISO standard 14044, the functional unit, when we want to define the functional unit, it could be better to select a functional unit after answering these questions: what, how much, for how long, how many times, where, how well. So the right functional unit for our study should answer to these 5 questions. If our functional unit answers to these 5 questions, probably the selection of functional unit is right. Okay. In the next slide, we have an example about this topic. In fact, in this case, the point is to compare 2 different outdoor paints. And so, in this case, the selection of 1 liter of paint as functional unit is not very is not the best option for the comparison of these 2 outdoor paints. But instead, if we read this slide, the definition of the functional unit, the right definition of functional unit, should answer to the previous 5 questions. In particular, a possible option for the functional unit in this case is, for example, this one: complete coverage of 1 square meter primed outdoor wall for 10 years in Germany in a uniform color at 99.9% of opacity. By defining in this way the functional unit of our outdoor paints, we can answer to the 5 questions, because to the question about what, the answer is complete coverage. How much? The answer is 1 square meter. What? Primed outdoor wall. For how long, how many times? The answer is for 10 years. Where? The answer is in Germany. How well? The answer is in a uniform color at 99.9% of opacity. So in this case, this functional unit was defined in a very detail. So not in all cases, not in all LCA studies, we can have this situation. In other cases, we can define in a more simple way, obviously, the functional unit. But when we have the problem to compare 2 products with different technical characteristics, different technical properties, this kind of definition, this way to define the functional unit is the better way if we want to obtain a meaningful comparison between our products. Okay. Sorry. Okay. Here in this slide, instead, we can read some common types of mistakes during the definition of a functional unit of a study. For example, in the first point, the first point is about the selection of a right functional unit when we want to compare the environmental performance of two different packaging. Okay. So in this case, if we select as a functional unit, for example, 1 kilogram of packaging material for our comparison, this choice is wrong, is absolutely wrong for the LCA study, because in this case, the physical quantity, the mass of packaging material is not a function. In fact, the mass required to provide a packaging function depends on the material. So in this case, the best option to choose the functional unit, to define the functional unit, is not 1 kilogram of packaging material, but for example, it could be 1 kilogram of delivered product by each kind of packaging. So in this case, the selection, the functional unit is meaningful for our comparison, because for example, if we choose 1 kilogram of packaging material, we have some problems, because for example, if we want to compare glass and PET in beverage packaging, these two materials have different density, different physical properties, and so different masses. And so in this case, this functional unit cannot be used to compare these two different packaging. But 1 kilogram of delivered product by the packaging is I repeat, is the best option in this case. In the second example of this slide, for example, the selection of this kind of functional unit enable watching of television with a 30 watt power consumption for 10,000 hours. Also in this case, this kind of functional unit is too restrictive if we want to compare two different TVs, two different televisions, because we defined in our functional unit the exact value of power consumption, but the power consumption is not important, is not relevant to the user of a television. So in this case, the right functional unit could be watching television for 10,000 hours. In this case, the comparison is all right, but not defining also the power consumption, because the power consumption depends on the efficiency of the product, of the television. So in this case, this kind of functional unit is too restrictive for for our aim. Okay. The third point about the scope definition step is the definition of reference flow. In this case, we can read the slide. When the functional unit has been defined, the reference flows can be determined. A reference flow is the product flow to which all input and output flows for the processes in the product system must be quantitatively related. So the reference flow is the amount of product that is needed to realize the functional unit. For example, if we consider the previous example about the comparison of two different outdoor paints, in this case, we have defined the functional unit as complete coverage of 1 square meter, blah, 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 blah. But now, if we want to compare two different paints, paint A and paint B, produced by two different companies, it is also important to define the reference flow associated to this functional unit. So, which is the reference flow in this case? We have to define the amount of each paint to obtain the complete coverage of 1 square meter for 10 years in Germany in a uniform color at 99.9% of opacity. Because the amount of paint A and paint B to reach this functional unit to reach this aim could be different, no? Because the technique, the parameter, the properties of the paints could be different. And so in this case, for example, here we can see, we can read that, for example, about for paint A, 0.67 liters of paint are necessary to reach, to realize the functional unit. Instead, for paint B, 0.15 liters are necessary to reach the same aim. So 0.67 and 0.15 liters represent the reference flows for a product A and product B. So the definition and the determination, the calculation of the reference flow is also another important parameter to consider when we want to compare two different products. Okay, in this slide, yeah, we have another interesting example about the definition of reference flow. In this case, in this example, we want to compare the environmental performance of a disposable cardboard cup with a ceramic cup. In this case, when we want to define the reference flow, we have to define the number of times the two cups are used before they are discarded, and how the ceramic cup is cleaned. So in this case, the reference flow is the definition of the number of times for the two products, for the two cups. So fourth point about the scope definition. So in this case, the fourth point is about the definition of system boundaries of the study. Also, this point is a very important point. In particular, we have seen in the last lesson the definition of technosphere and the difference between a technosphere and ecosphere, no? So we have said that technosphere includes all man-made processes. Instead, in the ecosphere, we find only natural processes. So when we defined the system boundaries for our LCA study, the aim is to define the boundaries between the studied product system and the technosphere and the ecosphere. In particular, when we want to define the system boundaries, we have to decide which processes are included in our LCA study. In the last lesson, we have said that typically each LCA study is characterized by 5 main steps, from raw material acquisition, extraction, up to the disposal stage of the product. But we, according to the ISO standard, we have the possibility to change these system boundaries, to strict the system boundaries for our LCA study, by considering, for example, only some of these 5 main steps. But the important thing is that we have to define in our report, at the beginning of the report, which kind of processes are included in our study. Obviously, if we decide to not consider some steps of the life cycle of the product, obviously we can obtain only partial results in terms of environmental performance of our product. So in this case, we want to focus our attention only to some steps, some phases of the life cycle. But it's important that the reader can know the hypothesis of your study. So the setting of as a report, as in this slide, the setting of the system boundaries can have an important influence on LCA results, because they determine the unit processes from which environmental impacts should be quantified. So as we have said in the last lesson, one of the first steps in the LCA, the practical step in the LCA, is to define the flow diagram of the unit processes, about the unit processes of our life cycle. And so at this step, we can define the system boundaries by including or by excluding some unit processes from our life cycle. According to the ISO standard, we are free to select we don't have a specific limitation about a specific indication by the ISO standard about the selection of system boundaries. Okay, we have the possibility to select 2 steps, 3 steps, 4 steps. We have only to define this choice in the report, but we are free to all possible options, to choose all possible options. And another important point in this slide, we can see the this figure that we have seen in the last lesson. In particular, in this case, in this figure, you can see that our flow diagram is constituted by different unit processes, and by these blue lines, you can see the elementary flows between technosphere and ecosphere. We have defined these blue lines in the previous in the last lesson. But another important aspect in the selection of system boundaries is that at the beginning of the LCA study, we can decide to define, to include all, for example, unit processes of the life cycle of the product. But when we in the following step of the LCA, when we will find the inventory data, input and output data for each unit process, in this step, in the inventory step, if we find, for example, that for some unit processes we don't have the possibility to collect input and output data, so in this case we have the possibility to return to this step of the LCA in order to exclude these unit processes from our study by justifying this choice in the report, but we are free to change the system boundaries, and so we are free to I repeat, to include or exclude some unit processes from our study. On the other hand, as I have said in the last lesson, if the aim of the study is to obtain an environmental label by carrying out the LCA study, so in that case, we are not free to include or exclude unit processes from our system boundaries. In that case, we have to follow also specific guidelines for our product, specific LCA guidelines, in which these guidelines define exactly which unit processes are to be included or excluded from our study. So the aim, and so the way to select to define the system boundaries depends on the final aim of the LCA study. So about the system boundaries, we can consider three different types of LCA. The first one, cradle to grave, that is the full LCA from extraction of raw materials up to the disposal phase, called as grave. The second option is the cradle to gate study. In this case, we don't consider the final steps of life cycle. So the use phase and the disposal phase are usually omitted in the study. And the third option is, for example, the so-called cradle to cradle study. In this case, this kind of study is a specific kind of cradle to grave assessment, where the end of life disposal step for the product is a recycling process. So when the product is recycled in the same process, so in this case we can define our LCA study as a cradle to cradle study, but typically the first two options are the most used types of LCA studies. Okay, this is not very important. Yeah, here, for example, we have another example in a comparative LCA study of 4 windows. The processes involved in cleaning the windows throughout their user stages can be excluded from the system boundaries of each window, because users are expected to clean the windows that all have the same surface area in the same way, using the same amount of water and detergent. So this is another important point when we want to decide the system boundaries for our products, because if the aim of the study is the comparison between two different products, but if for these two products some of the unit processes of the life cycles are in common with the two products, in this case we can exclude we can omit from our LCA study, from our comparison, the unit processes that are the same, because obviously the environmental impacts associated to these identical processes not change the final environmental results for the two products. So we have the possibility to exclude the identical processes for the two compared products. Only in this case. So the other point the other point is the cutoff rules. About the cutoff rules, this point in the definition of the hypothesis of the study is another interesting point, because we have the possibility in this section, we have the possibility to exclude from our analysis some data, some of the input and output data. We have said that the first step is the definition of the flow diagram of our life cycle of our product. Then we have to in the inventory analysis, in the second step of in the second phase of LCA, we have to define, collect input and output data for each unit process of our life cycle. So consumption of energy and materials, and the quantification of the amount of emissions in air, soil, water, and the waste is generated by the life cycle. But from this long list, by considering this long list of input and output data, in the hypothesis of the study, we have the possibility to exclude some of these data from our analysis. And cutoff rules represent the way to exclude this data, and which are the options which are the criteria to exclude some of these data from our analysis. According to the ISO standard, we have the possibility to exclude some data by considering three different criteria. The first criteria is based on the mass of each data. The second criteria is based on the economic value of each data. The third criteria is based on the real environmental impact, the real environmental contribution of each data to the to the overall environmental impact of our product. So by applying one of these criteria, we have the possibility to exclude some of these data. For example, if we consider the first criteria based on the mass content, in this case, I don't know, we can say that, for example, in this case, we have to define a threshold below a mass threshold, below which the data can be excluded from the study. I don't know, if we have a product characterized by, if we want to analyze the LCA of a product with an overall mass of 1 kilogram, and then we find that we have the consumption of some materials for the production of this product. And one of these materials is characterized by a mass lower than 1% of the total mass of the product. In this case, we can decide to exclude these input data from our analysis. For example, if we have for the product, we have the consumption of a small fraction, a small amount of steel. For example, 1 gram of steel is necessary to produce 1 kilogram of our product. So this amount is 1 gram, is lower than the defined threshold. In this case, the defined threshold is 1% of mass. So in this case, we can exclude this 1 gram of steel from our analysis. So we can omit from our analysis these input data. In this case, we have defined a mass threshold equal to 1% of total mass of the product. This is an option to define the cutoff rules for an LCA study. Another option is the definition of an economic threshold to exclude some data from the analysis. In this case, this threshold could be, I don't know, 1%, but this 1% is not in a mass term, but this 1% is on the economic is based on the economic value of the product and of the materials. So if we return to the previous example, our main product, the weight of our main product is 1 kilogram. The weight of the steel used for in order to produce the product is 1 gram. But for example, if the economic value of the product is equal, I don't know, is equal to 1 euro, and the economic value of 1 gram of steel is equal to 0.5 euros. In this case, if I decide to select an economic threshold equal to 1%, it's not possible to exclude this input data from our analysis because 0.5 euros is a value higher than 1% of 1 euro. That is the value of the product. So according to the mass criteria is possible. According to the economic criteria is not possible in this example. Okay. But according to the ISO standard, we have the possibility to select one or the other one criteria for the definition of the cutoff rules for our study. The last option is the definition of a threshold, not based on the mass content, not based on the economic value of the product and of the data, but on the effective contribution, environmental contribution to the environmental global impact of the product. So in this case, 1%, the threshold of 1% is referred to the environmental impact of 1 gram of steel. For example, if we consider greenhouse gases emissions associated to our product, and if at the end of the study we calculated that the greenhouse gas emissions associated to 1 kilogram of product are equal to 1 kilogram of CO2 equivalent, and if we have set a threshold equal to 1% of the effective environmental contribution, so if 1 gram of steel is characterized by an environmental impact higher than 1%, then 1% of 1 kilogram of CO2 equivalent, in this case, this contribution cannot be considered. In this case, the contribution of 1 gram of steel should be considered in our. Instead, if its impact is lower than 1% of 1 kilogram of CO2 equivalent, in this case, we can exclude this contribution from our study. So the third option is the best option, also according to the ISO standard, because in this case, we are sure that the approximation of the error associated to our final results will be lower than the first two options, for which we exclude some input data according to the mass or economic value of the data, but we don't know if its contribution is higher or lower, is high or low, and so only with the third criteria we have this possibility, to have the real idea of the environmental contribution of our input data. Typically, this threshold is based on 1% for mass, for economic, and for environmental contribution criteria.
I would have a question about this.
Okay.
Actually, a couple of questions. The first one is the percentage should be the same if I decide to use more than one, because there is the possibility. Okay, the percentage should be the same, so 1%, for example, or can be, for example, for mass 1% and for economic value 0.5%.
No, typically in the, for example, in the scientific studies or for commercial studies for companies, typically 1% is the most used threshold. Also, the possibility to define cutoff rules is permitted also in the specific guidelines to obtain the environmental labels. Also, in that case, we have the possibility to define cutoff rules according to one of these criteria. Typically, in that case, mass criteria is the is the option defined in these specific guidelines. And also in these specific guidelines, the threshold is always equal to 1%. But if we want to simply carry out the study according to the ISO standard, we can select other different threshold. The aim other different thresholds. So you can define 1% or 0.5 or 2, even if I don't know, 5%. Obviously, if the threshold is high, the quality of the final results will be low. Okay, so
Yes,
the idea is to define a low value for this threshold. The idea is to define a low threshold for this a low value for this threshold, but you are free to select different kind of values, but typically 1%. Okay.
Okay. And one more question is, if I decide to keep more than one criteria, so I stay on mass and economic value.
Yeah.
If the inflow is under the threshold of mass,
Yeah.
but over the threshold of economic value, what should I do? I should cut it off, or should include it?
Okay. In a study, you have to define only one criteria. Okay, you have to define only one criteria. So at the beginning of the study, you have to define mass, economic, or environmental contribution. But you have the possibility, as in the following example, in the next slides, we have the possibility to apply all three criteria. For example, if we want to have the security to not exclude some important data. So typically in the study, you choose only one criteria, but you have the possibility to apply in the same way all criteria. And so if you want to verify your choice by considering all the three criteria, if you obtain that, for example, for mass criteria, your value is lower than the threshold, and for economic value, your value is higher than the threshold. In this case, you can decide, for example, to include the data in your analysis. Okay, in this case. But
okay, clear.
It's not necessary to apply at the same time all three criteria. Okay.
Yes. I got it. Okay, thank you very much.
Okay, we can break. So break for 15 minutes. So
okay.
Now
Professor, did the lesson start back? Because it's on mute. Your microphone is on mute.
Sorry.
Oh,
So I
wasn't sure.
I didn't see the microphone. So briefly, we now we'll see an example about the application of the cutoff rules to the manufacture of a steel widget. In particular, in the table, we'll see the list of material input data for the production of this kind of product. And for each material input, we have data about the mass, the energy consumption to manufacture each material, and the environmental impact associated to each for the production of each material input. Environmental impact expressed in terms of kilograms of CO2 equivalent. So in this case, the environmental performance is calculated only on by considering the greenhouse gases emissions, only by considering the climate change impact category. So previously we have said, sorry, because I have a problem with, I don't know. Okay. So previously we have said that we have the possibility to select one of these three criteria, but in theory, we can also consider another option for the cutoff criteria. The other possible criteria is based on the energy content of the input materials, as in this column, no? But the meaning is the same. In fact, in this example, we have three different options for our cutoff rules. The first one, inputs contributing less than 1% of manufacturing stage mass inputs will be excluded. In the second option, the threshold of 1% is referred to the manufacturing stage energy input. And as regards the third criteria, in this case, we can exclude by the analysis all input data characterized by an environmental contribution less than 1% of the overall environmental impact associated to the product. In this table, we can see the application. In the first table, we can see the contribution, the percentage, the mass contribution, the energy contribution, and the greenhouse gases emission contribution of each input data to the total. So from the first table, we can see that, for example, I don't know, the second material, cutting fluid, has its contribution in terms of mass is lower than 1%, but for the other two criteria, its contribution is higher than 1%. Only for one material input, steel fasteners, we have the situation for which this input data is characterized by a contribution in terms of mass, energy, or environmental contribution less than 1%. And so if we want to consider all these three criteria, if we want to assume at the same time all these three criteria, in this case we can exclude from our analysis only one material input, only the steel fasteners, for which we have a contribution less than 1% in mass, energy, and CO2 emissions. Okay, the other point in the scope definition step is the data quality, is the definition of the data quality requirements. Also, this point is a very important point for LCA, because we have said that during the second phase of LCA, the inventory analysis phase, during this phase, the LCA practitioner should collect several data about input and output data. But in the last lesson, we have said also that we have the possibility to find these data from direct measurements in the company, so primary data, or secondary data obtained from databases. Okay, but in particular, as regards the secondary data, so as regards the data from databases, it's important in this step, in this phase of LCA, it's very important to define the data quality requirements for these secondary data, because not all databases are useful for our LCA study, but depends on the object, depends on the aim of the study, and in particular, according to the ISO standard, the data quality requirements are defined by considering three different dimensions: geographical requirements, time-related requirements, and technology requirements. So at the beginning of the study, we have to define all these requirements for our secondary data. So, for example, as regards the first point, the geographical dimension, geographical data quality requirement is the area from which data for unit processes should be collected to satisfy the goal of the study. For example, if you want to analyze a product manufactured in Italy, or in general in a European country, it's important that the secondary data used to model the inventory of this life cycle, it's important to consider a database typical for the European context. And so in the commercial LCA software, we can find different databases with different names, with different processes. And for example, for the European context, the most used database is called EcoInvent. EcoInvent is the most important database for LCA for the European context. But if we want to analyze a product in the United States or in Australia or in China or in other part of the world outside the European boundaries, in those cases, we cannot use EcoInvent database to collect, to find data for our inventory. In those cases, we have to use other databases typical for United States, for Australia, for China, and so on. So the definition of geographical data quality requirements is very important to this scope, to this aim. We don't have specific databases for each country. Actually, we don't have a database, for example, only for Italy, only for Germany, only for another, in the case of European countries, for a specific European country. And so EcoInvent database can be used for all processes inside the European countries, okay? But outside, we have to use other databases. This is the first point. About the second point, time-related data quality requirement. In this case, we refer to the age of data and the minimum length of time over which data should be collected. So, in this case, we have to consider that each database, each process in the databases was made some years ago. So we can have, for example, databases with processes made, I don't know, 10 years ago, 20 years ago, and so on. So it's important to define the age of data useful for our LCA in order to select the best database. So if, for example, for the process of I don't know, cutting wood, we find this process inside the EcoInvent database, but we find that this process was made with data of 10 or 15 years ago, and we want to analyze this process now. Actually, probably this process cannot be used to model our LCA because this process was made several years ago. Okay, this is the problem. So we have to define also, when we decide to carry out an LCA study, we have also to define the maximum age of data. Okay, the maximum age of data. About the third point, the technology data quality requirement, this requirement is correlated with the previous one, with the time related requirement. In fact, in this case, we have to define which technology should be considered to model our life cycle. Here, I think that we have an example in this slide. For example, crude steel can be produced using an electric arc furnace or a basic oxygen furnace. So if we have this kind of process inside our life cycle, we have to define in this step, in the scope definition step, we have to define which technology should be considered to model the crude steel production process. Because probably, for example, in the database, for example, in the EcoInvent database, we can find both processes for crude steel production, based on electric arc furnace or based on basic oxygen furnace. So the choice depends on the hypothesis in this step of the LCA. Okay, this is valid not only for this example, but for all technologies inside our life cycle. Okay, this is an important point. Okay, here you can see some details about the geographical requirement. So we can read, for example, differences between unit processes can be caused by geographical differences such as local climate, proximity to natural resources, or, for example, different policies. And at the end, it's interesting to read the last sentences. For example, the electricity mixes of Denmark, mainly coal and wind power, and Sweden, mainly nuclear and hydropower, vary quite a lot despite the close proximity of the two countries. So it's very important to define the geographical context of our study in order to find, in order to collect data that can be that can represent our situation. Okay, I think that in this slide also other about time related requirement. We have said previously the so, for example, in this slide, a unit process that reflects the situation 10 years prior to the occurrence of the process in the product system can have a high time related representativeness if it belongs to a mature sector with little technological innovation, such as the pulp and paper industry, but it can have a low representativeness if it's part of a sector with a rapid technological development, such as IT, energy, and so on. So the choice of the age of data depends also on the type of product to be analyzed. So for example, if we have a product with a little technological innovation, probably also data with an age of 15 years could be useful for modeling our process. Obviously, in the energy or IT sector, this is not valid. Okay. Okay. Yeah, this is not very important. We have said previously, technological. Okay. Yeah. So the last point, typically is not very easy to understand. So it's important to stress this point, to highlight and to explain better this point. This point is another important point in an LCA study. How we want to model multifunctional processes. First of all, we have to define a multifunctional process. A multifunctional process is a process characterized by two or more than two functions. So, for example, when we have this situation, we can have this situation when we have a process from which we have the production, the generation, not only of one product, but we have the generation of at least two different products. Do you have an idea of an example of this kind of process from which you can we can have two different products? Do you have an idea about this kind of process? In this slide, you have, at the end of the slide, you have an example, but you have several examples in other contexts. The same example about the wood. If you use wood, for example, to produce construction wood, okay, if you use wood for the production of construction wood, you have the for example, the cutting phase of wood, no? And from the cutting phase of wood, from this process, you can have two different products. Construction wood, but the second product is the wood powder. Okay, wood powder. Wood powder is not a waste, but it could be considered as a byproduct of the cutting wood process. And so in the LCA, we have to define, we have to consider that a product from a process is considered as a byproduct of the process if it has an economic value. Instead, if it does not have an economic value, okay, in this case, this product, this secondary product, should be considered as a waste. This is the difference, okay? So a multifunctional process is a process from which we can obtain at least two different products with economic value, okay? So in this example of cutting wood, we have two products because also wood powder has an economic value, because wood powder could be used for energy purposes, for example, okay? But I don't know, if you have a process from which you have a you have a waste, and this waste should be disposed, for example, in landfill. In this case, this process is not a multifunctional process. Okay, this is a simple process. It's a simple process. Okay, this is the difference. Okay, and this is the definition of a multifunctional process. So secondary functions, we can read, are unintended functions that usually have low or no relevance to the users of a product, meaning that they are not contributing to the obligatory or positioning properties, as in the example of cutting wood, because my main aim is the production of construction wood, not the production of wood powder. Wood powder is only a secondary function of my process. Okay. At the end of this slide, you can read another typical example of a multifunctional process. No, for example, in this case, the process is the animal husbandry. In this case, from animal husbandry, we can obtain several products, such as milk, meat, hide, bone meal. All products have an economic value. So animal husbandry is a typical example of a multifunctional process. Okay, is it clear, this definition of a multifunctional process? So from the definition of multifunctional processes, now we have to understand how these kind of processes are modeled in the LCA. For you, which could be the problem to model in the LCA this kind of processes? Which could be the problem? So we have we know that the aim of the LCA study is to calculate the environmental performance of a product. So we or for example, in the case of animal husbandry, I don't know, we have our aim of our LCA would be the calculation of environmental impact for the production of milk, no, or for meat, but we can consider for milk. So our main, the main product for us, for our study, is milk. The other products are secondary products, byproducts. So which could be the problem to model, to consider in the LCA the other products, the secondary products, because the animal husbandry will be characterized by a list of input data and output data. Then these input and output data will be put inside this so-called black box, an impact assessment method, to calculate the final results. So to calculate, for example, the greenhouse gas emissions associated to animal husbandry. Okay, but which could be the problem? If we have several products from the process.
The input and output data is from
okay, but yeah, this is a good idea, but we are, in this case, in this example, we have a problem, because you have said, I think, that you want to divide the input and output data in order to find which data are due to milk, or are due to meat, or are due to height, or are due to other product. This is your idea, no? But this is a problem in this case, because the process of animal husbandry, it's not possible to divide the animal, because animal husband, all products derive from the same animal. And so we have not the possibility to, we don't have the possibility to separate the animal, a part of animal for the production of milk, a part of animal for the production of meat. This is not possible in this case. And so the problem is that, for example, no, I don't know if I have a, I don't have a, nothing. Okay, right. I will try to explain only by words. Sorry?
I think the Zoom, they have the whiteboard for you.
Ah, okay. I don't know. Huh?
Maybe the pen.
Yeah. Yeah. So, but okay, it's not very easy to write with mouse. Huh? It's not very easy. So it's no, for me it's very difficult. For example, you have input and output data for animal husbandry. You have from this list of input and output data, you have calculated a greenhouse gas emissions equal to 10 kilograms of CO2 equivalent. That is the unit of measure for climate change impact category. Okay, so the first question is, this value of greenhouse gas emissions, 10 kilograms of CO2 equivalent, are due to milk, are due to milk, meat, hide, and the other products, which is the answer? Are due to milk, only to milk, or are due to milk and the other products? Yeah. So 10 kilograms of CO2 equivalent, for example, per 1 liter of milk, that is our functional unit. These 10 kilograms of CO2 equivalent are due not only to milk, but are due also to the other products. So we want, the idea is to divide, no, these 10 kilograms of CO2 equivalent between milk and the other products. This is the aim of modeling of multifunctional processes. Now we have to understand how we can divide the criteria in order to divide these, to attribute these 10 kilograms of CO2 equivalent to the different products. This is the problem, okay, now. And in the next slides, we'll see which criteria we can apply according to the ISO standard to divide these 10 kilograms between the main product and the byproducts. Okay, this is the the aim. Yeah, here you can see, you can read another example of a multifunctional process. For example, the waste incineration process. In this case, for example, from burning wastes, we can obtain two different forms of energy, electricity and heat. And in this case, if we want to analyze the environmental performance, the environmental impacts associated to the production of 1 kilowatt-hour of electricity from the combustion of wastes, in this case, electricity is our main product and heat is our byproduct. But we have the possibility also to consider the other situation. If we want to analyze the heat from waste combustion, in this case, heat becomes our main product, and instead electricity becomes our byproduct. So depends on the functional unit and depends on the aim of our LCA study. Okay, so product and byproduct depend on the functional unit of the study. Okay. Yeah, this is yeah. We can go. This is the example of previous example about electricity and heat. Yeah, I want to. Okay. I want to see now the criteria in order to separate, in order to divide the impact between the main product and the byproducts. So this figure is drawn from the technical ISO standard. We have different possibilities to divide this environmental impact between main and the other products. The first option is your option. In this case, this option is called as subdivision of unit process. So in this first option, you have to find, you have to evaluate if your unit process could be divided in some sub-unit processes in order to find which input and output data are related to the main product and which input and output data are related to the byproducts. But for example, for animal husbandry, this is not possible because we cannot divide the animal in because in milk, meat, and the other products are obtained from the metabolic process in the cow. So it's not possible to divide the input and output data. But we can have some situations in which this unit process can be divided into some sub-unit processes. And so in this case, we have the possibility to identify which materials and which emissions are associated to product one and which materials and which emissions are associated to product 2. This is the first option, and probably if it's possible, it's the best option to model the multifunctional processes. But if this option is not possible, we have the second one option. So the first one is the best. The second option is the second best option. And then we have the last options. In the second option is called as system expansion approach. So we can explain this approach with an example. Then you can read the definition in the slide. But I think that it could be most important. It could be important to consider an example to understand this kind of approach. So, but in this case, we can try to write something in the slide. Okay. So we have our unit process. From our unit process, we can consider the example of animal husbandry. Okay. Animal. So from animal husbandry, we obtain, for example, 2 products, only 2, milk and meat. It's very difficult to write with mouse. Huh? Very, very difficult. Okay. In particular, we have from the input and output data associated to animal husbandry, we have calculated an environmental impact in terms of greenhouse gases of 10 kilograms of CO2 equivalent. Okay. And the aim is to divide this value between milk and meat by applying the system expansion approach. In this case, so we then will use this example also for the last options. So in this case, the idea, we consider that our main product is milk and byproduct is meat. So the idea is to find in the market another product that can be substituted by meat, by our byproduct. This is the idea. So in this case, for example, I'm not an expert of cows. Okay, I'm not an expert, but meat can be produced by cows dedicated to meat production, or can be produced by cows, from cows dedicated to milk production. So in this case, meat is obtained from cows dedicated to milk production. So in this case, this amount of meat, for example, I don't know, we have selected 1 liter of milk as our functional unit. For 1 milk of for 1 liter of milk, we obtained, I don't know, 0.5 kilograms of meat. So these 0.5 kilograms of meat obtained from a cow dedicated to milk production, probably in the market could substitute 0.5 kilograms of meat obtained from a cow dedicated to meat production. So in this case, if we want to divide these 10 kilograms of CO2 equivalent between milk and meat, we have to calculate the greenhouse gas emissions associated to the production of 0.5 kilograms of meat from a cow dedicated to meat production. If we calculate, for example, that the environmental impact associated to the other process, I don't know, 2 kilograms of CO2 equivalent is the impact for the production of 0.5 kilograms of meat from cow dedicated to meat. So now we can say that the effective impact associated to 1 liter of milk of our product will be 10 minus 2. Okay, so in this case, 8 kilograms of CO2 equivalent will be the effective impact for the production of 1 liter of milk. This is the idea, according to the system expansion approach. This approach can be applied in all cases, but in some cases, it's not very easy to identify the other product in the market, the substitute product in the market. It's not very easy. Another example, in the case of wood powder, okay, construction wood and wood powder, in that case, if we use wood powder for energy purposes, for example, for heat production, which is the substitute the other process in substitution to heat produced by combustion of wood powder, which could be the process in the market. Heat production, but not from the combustion of wood powder, because it's my process. But we have to find the typical situation for heat production actually in the market. For example, an option, it could be the heat production from natural gas. So the same, if we can obtain 1 kilowatt hour of heat, of thermal energy from the combustion of wood powder, we can calculate the environmental impact associated to the production of the same amount of thermal energy, 1 kilowatt hour, but by using natural gas instead of wood powder. The impact will be different. And so with the same principle, we can apply the system expansion approach, because we can calculate the impacts due to the production of thermal energy from natural gas, and then we subtract this impact from the environmental impact of cutting wood. In this case, we can obtain finally the environmental impact due to the construction wood. Okay, so also in that case, we can find a substitute product. Another example, if we have the process about the combustion of wood powder. In this case, our process is the combustion of wood powder in a, I don't know, in a boiler, in a residential boiler. So in this case, our main product is the thermal energy obtained from this combustion. For example, 1 kilowatt-hour is the functional unit. And from the combustion, the byproduct from the combustion of wood powder, which is the secondary product from the combustion of wood powder. If you burn wood powder in a boiler, you have the production of thermal energy, you have the emissions of flue gases, but also the residue of the combustion, ashes. Okay, the residue of the wood powder combustion is the ashes, but the ashes can be considered as a waste, but not only as a waste. They can be considered also as a byproduct with a potential, only potential, economic value, because ashes can be reused as a fertilizer in field crops, for field crops, as a fertilizer. Okay, and so if we consider ashes as a fertilizer, in this case, ashes become a byproduct of the wood powder combustion process. And in this case, we have to calculate the amount of chemical fertilizer that can be substituted by the application in the field, on the soil, by the application, by the spreading of ashes. So we can calculate this amount of chemical fertilizer, and then we subtract the impact from the total impact of the wood powder combustion process. The idea is always the same, okay? For today, it's all. Okay, so next lesson will be on next Wednesday, okay? Okay, bye-bye.
Thank you, Professor. Bye. Bye-bye.